open up your notes called Mathematical Modeling with Nonlinear Functions. We've talked about how to linearize exponential and power functions in order to use linear regression. Actually, you don't have to linearize them in order to use the calculator regressions, but that is why the calculator regressions contain R values. We learned that R represents the strength and direction of a linear relationship between two variables. The reason that exponential, power, and logarithmic functions have R values is because they can be written as linear relationships between x and log y, log x and log y, and log x and y. So in your calculators internally doing a linear regression, converting it to linear form, doing a linear regression, and then converting it back to its original, the original form of the data. We also said that quadratic and logistic don't have R values because they cannot be converted to linear form, but we have to just evaluate quadratic using R squared and logistic just by common sense in the shape of the function. Now, what happens though if we use get a set of data, try several of these functions, and it's really hard to tell from their R value which one is the best? What else can we look at? And we're going to talk today about endpoint behavior. So turn to the next page in your packet, the one that says endpoint behavior. Okay, you'll see some data over here. I want you to make a scatter plot on your calculator. So remember, that means we need to go into your calculator, add a list and spreadsheet. I need to kind of reposition this. Add list and spreadsheet and enter that data in. We'll just call this X value using, notice that to do an underscore you can do control and then this button right here to do an underscore. I'm just going to call it X value and Y value. Your calculator seems to prefer not using a single variable for a list name, so that's why I'm going to do that. And then when we look at the data here, 2468, oops, it didn't take here. Let's try this again. 2468 and 4.5. I'm rushing a little bit here. 7.5. So you should be doing this along with me on your calculator because you need to be able to know how to do this. So if you haven't gotten your calculator out, I'd pause and get that out and get this data entered in. Then we're going to go ahead and go to a data and statistics page. So control doc, not control menu. Come on, behave yourself, calculator. Okay, so data and statistics page, and I'm going to click and put my X value on the X-axis and my Y value on the Y-axis. So I have here a set of data. You can see it's fairly straight, has a slight curve to it. There's a number of different functions that might be able to fit this data. So we're going to try a bunch of different regressions. We're going to do a linear, an exponential, power, logarithmic, quadratic. So if you go back and look at your notes, you'll see we are going to do all these different regressions, and we're going to record the R and the R squared values for each of those. And then we're going to look at what's called the endpoint behavior. So this is, I'm going to do a couple of I'm going to go through one of these maybe, and then I'll probably pause and let you go ahead and do all of the work for filling in the R values, and then come back to the video for the grand finale. So let's go ahead. We can go ahead and do a linear regression. Just to remind you how to do that, you go to Menu, Analyze, Regression, and then you can choose. I actually grabbed the wrong one here, so let me delete that. And if you just push delete, you can get rid of it. So Menu, Analyze, Regression, and then I'm going to go to my linear regression first. And there's the equation. Now, how do you find the R value? Well, you're going to need to go to open a document page, open a calculator page, and then you're going to want to do a linear regression. However, there is a shortcut. If you just want to find the R value, go to the variable button, and under the variable button you'll see stat R right here, and push enter, and there's the R value. Now, that R value will change every time you do a regression. So that R value is good for the linear regression that I just did, but then when I do another regression, when I go back and find stat R, it will be for the latest. So you can't do a bunch of regressions and then go back and find all the R values. You have to find the R value each time you do a regression. Okay, so now I'm going to look at, there's my linear regression, and I'm going to go ahead and delete that. No, actually I'm going to leave it on. Then I'm going to go to Menu and Analyze and Regression, and now I'm going to do a quadratic regression, which is number 4. Or let's see what's next. Let's do exponential. That's the next on the list. So go to 8. Now, which one do you think fits better? Kind of hard to say. They both aren't perfect, but they both fit the data pretty well. So let's go back to my, if I go to my calculator page and I go to variable and go to stat R, now it will give me the R value for, it should give me a different one. So there's my R value for the exponential regression that I just did. Go back to menu and you can, I'm sorry, I need to go back to my calculator page or my graph, and I'm going to do another regression. Now the reason I'm doing them all at the same time and not taking them off is for a reason. So go ahead and do them all at once. The next one is a power function, so we'll go to 7. Okay, that's the dark line. Once again, seems to fit pretty well. It's not bad. Going back to my calculator page, going to my variable button, going to my R value and enter. Look at all those R values. They're all really, really good. They're all really close to 1. You can't really say that 9.9 and 9.8, 0.99 and 0.98 are all that much different from each other. As a matter of fact, the 0.986 rounds to 0.99. They're all very strong. There's very little residuals. The residuals are very small. All the points are close to the line. So it's kind of a toss-up between all of these. Which one is the best model? Okay, let's go to logarithmic now. I said I was going to do these separately from you, but I guess I'll just do them along with you. So let's do logarithmic. So menu, analyze, regression, logarithmic. That's number 9. Now when I look at that one, it seems to curve in the opposite direction from the data, so that one I'm not as thrilled about. Let's check out the R value for that one. Okay, so if we go to variable and go down to R, the stat R. Okay, notice that one's significantly different from the other 3. So I could probably say I don't think logarithmic is a good choice here, but the other 3 are still good choices. Okay, back here, let's do the last 2. We're going to do a quadratic and logistic. So menu, analyze, regression, quadratic. That's number 4. That's the darkest one, remember. That's the one we've just done, is this darkest one. Not bad. That's kind of in the way. Let me get this out of the way. That seems to fit really well through all. It goes through actually all 4 of the points, so that's not bad at all. If we go to our calculator page, now remember quadratic doesn't have an R value, so notice when we go down there isn't even a choice of stat R, but we can do R squared. Now remember R squared is just the square root, it's the square of R, so it's still a really strong R squared. Also you want to be close to 1. Now R squared obviously is, since it's squared, it's always going to be positive, so the smallest is 0 and the largest is 1, but if it's close to 1, that's very good. So once again, quadratic looks like a possible function for this data. Okay, last one, logistic. So let's try logistic. Logistic's kind of a tricky one because logistic is, because of the way it curves, you can make it fit almost everything. So with logistic, you have to think more about, does it make sense? I think we're going to have to go down to find logistic. There's logistic. Logistic where D equals 0, logistic where D is not equal to 0, and I'm trying to remember which one I want to use. Let's try this. Let's do C. Actually, I think it was the other one I wanted to use, so I'm going to go back. Let's push delete on that one. It's the most recent one. Let's see if I can click on the actual line here. Okay, I do think I deleted it because that's the quadratic that I'm seeing right now. So let's go back to menu and analyze. I always forget which of those I want to use. Regression and logistic, and we're going to do the logistic where D is equal to 0. Enter. Okay, so that's the curve line. Once again, that looks like it fits pretty well. If we go to our calculator page and we go to var and push, notice we don't have r or r squared, so there's nothing I can do to check the residual for that, for my logarithmic. So with logarithmic, I have to look at fit, and I have to look at whether or not it is a reasonable thing to use for the data. And we'll talk more about reasonableness in an activity we do when our practice modeling activity. Okay, so far we have found everything but logarithmic looks like it fits really, really well. Logarithmic, that's this one right here. There's our logarithmic. That one's curving the wrong direction, but all the rest of them look pretty good. They all are reasonably close to the data. So what we want to find out now is check endpoint behavior. So what we're going to do is we want to know what happens if we were to extend the graph out and see more of what these lines do. So what we're going to do is change our window settings. So go to menu, go to your window settings, and we're going to change our x-min from 0, because we want to see what happens at 0, to 50, and our y-min 0 to our y-max 100. Push enter. Oh my gosh, look what happens to these equations now. So let's see. Notice if we're looking at just where the data is, if we were interpolating, if we were predicting within the data value, all of these lines would give us pretty good approximations. Even that logarithmic that didn't seem to fit very well, it's not bad actually. But if we go beyond the data, my gosh, these are so different. If we were to put in, try different predictions here for different values, like when x is 50 or x is 45, notice if x were 45, look at how different the y values would be for that. I mean, this one would be so extremely high up there. It would be incredibly high. So let's look at what these different functions are. This bottom one here, this one that's highlighted, is the logarithmic function right there. We clicked on this one. That one's the exponential function. Notice the x in the exponent position. There's the I'm sorry, that's not the exponential. That is the logistic. So logarithmic, logistic. Notice what the logistic function does. You know what, I think I have two different logistic functions on here because I think this one is also a logistic function. Yeah, that's the one I really didn't want. I'm going to delete that one. I thought I had deleted it. Okay, there we go. Alright, so this is the logarithmic function, which we said it looks like it curves the wrong direction because the data is curving up and it's curving concave down, and the data is concave up, so we could pretty much eliminate logistic. I'm sorry, logarithmic. Here's logistic. Now logistic curves the correct direction and then it levels off completely. Remember, logistic is the one that has a horizontal asymptote. Well, is that reasonable for the data? Don't know. I don't know if it is or not. So it depends on what the data is about. Here is our, I believe this one's our linear function. Yeah, there's our linear function. It appears that the data is curving, so I would say probably linear doesn't seem appropriate. Then we have three functions that do curve upward at different rates. So this one right here is our power function. Here's the quadratic, and here is the exponential. Notice the exponential is the fastest growing function. If you use exponential, you're talking about an extremely high rate of change as x gets bigger. So which one makes the most sense for the data? I don't know. See, this is where you need to know the context of the data. You need to know what happens, what's reasonable to happen. Is it reasonable to assume a constant rate of change like linear? Is it reasonable that the rate of change would be this rapid as with exponential, or would something sort of in between be more reasonable? Is it reasonable to think that the data would completely level off and not get any bigger? or that it would change direction? Probably not. But what is reasonable? So that's what endpoint behavior means. What is reasonable for the data? So what I would suggest you do on your notes would be to make a little sketch of this, of what the endpoint behavior looks like, and label each one of your functions as to exponential, quadratic, power, linear, logistic, and logarithmic, so that you can see what happens in the long run with different types of functions.